After studying this module, you shall be able to know about how the latent fingerprints can be enhanced by certain chemical reagents, how the optical light sources help in the enhancement of fingerprints, and also learn about the various alternatives that can be employed for their detection and visualization. In spite of the scientific developments done in the field of DNA profiling, fingerprints remains the best and a crucial form of evidence needed for the personal identification in the arena of crime scene investigation. Fingerprint detection has improved significantly over the last 20 years due to concerted efforts by a number of research groups around the world. A wide range of optical, physical and chemical techniques are now available for the detection and enhancement of the latent finger marks. The best results are generally obtained if a logical sequence of technique is applied. Also, in case the fingerprints, the application of various techniques or chemical reagent may increase the number of latent prints detected, thereby improving their quality and finally enhancing them. However, it is imperative that each process is applied in a systemic, predetermined order so that the incorrect choice or application of one method can preclude the later use of another technique or lessen its effectiveness. During the procedure for the latent prints detection, the employing of optical technique and procedure should be heavily emphasized, as these are non-destructive in nature and considerably improves the results obtained by physical or chemical method. Other techniques must be applied with caution and the developed prints recorded at each opportunity, as the finger marks are fragile and readily destroyed. The choice for the detection technique invariably depends on the circumstances from where the latent prints have been recovered from, and thus also depends on the variety of factors including the type of surface on which the latent print is present, that is whether it is porous, non-porous, smooth or rough, their occurrence of any specific contaminant, for example blood, the probable age of fingerprints, and lastly the environmental factors, example whether or not the surface is or has been wet. Now we will study about the fingerprint enhancement by optical technique and specialized light sources. The simple observation of any object under white light may disclose a visible finger mark, and that can be recorded without any further treatment. On the other hand, more complex optical detection methods may reveal otherwise invisible prints that may not be developed by other technique. A fingerprint detection sequence should always start with the optical technique. In addition, the prints developed using a physical or a chemical process can generally be further enhanced using an appropriate optical method or technique depending on the characteristic of the treated marks, for example the color or the luminescence property. The value of fingerprint luminescence has become well understood since it was first studied in the late 1970s. Although the property of luminescence is not seen in case of latent fingerprints, a variety of procedures and techniques applied in the correct sequence will thereby result in the generation of luminescent prints. The heavy emphasis on luminescence property is due to the much higher sensitivity that can be achieved when compared to the conventional processes that result in a colored print. The application of luminescence technique requires the use of high intensity light sources, and with large, expensive laboratory-based lasers were proposed in the early 1980s for this work. There are now a number of versatile, cost-effective alternatives, and as such, the filtered arc lamps also. Today, for the purpose of fingerprint detection and enhancement, polylight is used. This light source is portable and provides a range of high intensity light bands from the ultraviolet through to the near infrared range of particular wavelength. In addition, each band can be fine-tuned through the tilting of high quality interference filters built into the system. This function has now been duplicated in other light sources as well in the market, and alternatives to the polylight include the specs, the quasar, the dactylite and the portable lasers such as the scene sweeper. Lasers are restrictive in that they only operate at a limited number of wavelengths. As we already know that there are three main types of fingerprint evidence that may be present at any crime scene. The first is the indented or the molded finger mark, which is a three-dimensional fingertip impression in a malleable substance such as a putty or a candle wax. Such impressions can generally be enhanced using the oblique lighting. The second type is the visible finger mark, which may be positive or negative depending on whether the fingers were contaminated with a colored material such as blood or whether the colored material such as dust or soot has been removed from the surface by the fingerprint ridges. Enhancement of such marks can often be achieved optically also, depending on the properties of the contaminant in question. Blood is a special case where the specific optical and chemical enhancement procedures almost exit out. The third type, which is the most common and that poses a real dilemma, is the latent fingerprints. Latent fingerprints or the finger marks are not visible by the naked eyes and hence are usually requirement of some type of physical or chemical treatment and enhancement so that they can be easily detected and visualized for that purpose. These latent prints are formed from the complex mixtures of natural secretions secreted by the sebaceous glands and also from the contaminants from the environment. Knowledge of the major constituents of this particular deposit is essential for the effective fingerprint detection. Consideration of how these constituents are affected by the different environmental conditions is also an important parameter. The detection of latent finger marks is actually quite a challenging analytical problem. What is required is the detection of very small quantities of specific chemical compounds. In general terms, fingerprint powders are the least sensitive of the available techniques, with about 500 to 1000 nanograms of the material required in the latent mark for successful detection. By employing the usage of chemicals, for example ninhydrin, and such that the color can be imparted to the latent prints, generally 100 to 200 nanograms of that material is required. On the other hand, luminescence detection using a chemical reagent such as DFO is sensitive down to the range of 1 to 10 nanogram. The latent fingerprints deposited on the various surfaces behave differently on different types of substrate. Also, in addition to this, the various techniques employed for detection purpose are effective only on some surface but not on others. And as a result, the surface type is a major consideration when selecting a sequence of fingerprint detection technique for a particular set of circumstances. Next is the detection of fingerprints on porous surfaces and their enhancement. Following the application of optical techniques, the choice of development method will depend on whether or not the item has been wet. If the item has been wet, then water soluble component of the latent fingerprint deposit will no longer be present. In such a case, the physical developer will be the accurate method of choice. In other cases, the techniques that can be applied include the DFO, ninhydrin and metal salt treatment. The physical developer can then be applied at the end of the sequence. A chemical reagent that readily reacts with the amino acids present in the sweat, thereby resulting in the formation of a dark purple colored print, is the ninhydrin, also known as luminance purple. Ninhydrin as a fingerprint development chemical reagent was first proposed in the year 1954, and today it has become the most widely accepted technique for the latent fingerprint development on the paper surfaces. This technique generally involves dipping the items or spraying them with ninhydrin solution and then leaving them as such over for 24 to 48 hours for their development. Prints of more than 50 years of age have been developed in this process. Over the last 30 years, different carrier solvents for ninhydrin formulation have been proposed. The most well known and the most successful being CFC 113, also known as R clone of fluorosil. Being an ozone depleting substance, this solvent is no longer manufactured and its use is now prohibited in a large number of countries. Ideally, the carrier solvent should be non-toxic, non-flammable, non-polar, so that the ink running on the document is minimized and relatively inexpensive. Alternatives such as pentane or hexane are to be avoided because of their high flammability, and as well as being inflammable. Solvents such as acetone causes excessive ink running on the treated documents. Several research groups around the world have studied the CFC 113 replacement solvents such as HFE 7100 and HFC 4310, and a number of formulations based on these two alternatives are now in use. Unfortunately, both of these solvents are expensive, and which limits their use in some laboratories. Finger marks treated with ninhydrin can be further enhanced by a treatment with the zinc or cadmium salt solution. The coordination complex that is formed results in a color change and gives a print that is luminescent under certain conditions. At low temperature and with appropriate excitation from a high intensity light source, considerable fingerprint enhancement can be achieved. In the year 1990, the chemical reagent 1,8-diazine-9-fluorine-1-one, commonly known as DFO, became available as a more sensitive technique for fingerprint detection on paper. DFO reacts with amino acid in the latent finger mark in much the same manner as for that of the ninhydrin, and DFO can also be said as the analog of ninhydrin. However, heat is required for successful development and the reaction product is much paler in color than that of the ninhydrin. The advantage of DFO is that the developed prints are highly luminescent at room temperature without any additional treatment. Studies have shown that up to 3 times the number of fingerprints can be developed with DFO in comparison to that of the ninhydrin reagent. DFO can be used but not after ninhydrin processing. The disadvantages of DFO include the requirement of a specialized light source, the relative high cost of the reagent, and the unsuitability of the technique for luminescent substrates. Physical developer is a technique that can be applied on porous surfaces that have been wet or as an additional treatment after DFO and anhydride processing. PD is an aqueous solution similar to silver based photographic developer, and when a document is placed in the reagent, silver is deposited from the solution on any latent finger mark that may be present over the surface. This deposition is catalyzed by water soluble components of the deposit, and the developed prints appear as dark grey images against a light grey background. The PD solution contains a ferrous or ferric redox system plus the silver nitrate and citric acid stabilized by a surfactant. Once prepared, the solution is unstable and has a short shelf life. Although time consuming to prepare and apply, the PD can give best results where other techniques are unsuccessful totally. Even if the documents have not been wet, the use of PD or DFO and anhydride is advised for all serious cases, as it may reveal addition of the fingerprint detail. Now we will study about the detection of fingerprints in non-porous surfaces and their enhancement technique. Typical non-porous surfaces include glass, plastic, metal and gloss painted surfaces. A range of techniques can be applied to such surfaces depending on the surface characteristic. As for any fingerprint detection sequence, the optical technique should be employed before applying any other treatment. For fixed surfaces at the crime scene, powdering is still entrenched as the primary fingerprint detection method despite its low sensitivity. For wet surfaces at the crime scene, the small particle reagent can be employed as a wet powdering method applied with a spray. Items can then be transported and should be returned to the laboratory for processing. Cyanoacrylate fuming has since the late 1970s become a popular laboratory-based technique for the routine treatment of non-porous surfaces. The developed prints can then be subsequently enhanced by the application of a luminescent stain. Alternatively, for laboratories where it is available or advisable, the vacuum metal deposition can be particularly effective for older prints or for the difficult surfaces. Fingerprint powdering has changed little as a detection technique over the last 20 years. It is still the most cost-effective method for treating fixed surfaces at a crime scene, and a range of different powders and different brushes are available, and the choice generally comes down to personal preference based on the experience. Aluminium flake powders have long been considered to be particularly effective, while magnetic powders applied using a magnetic wand are considered to be the least destructive. The recent development of iron flake powder has increased the sensitivity of magnetic powders for use. For multicolored surfaces, a range of different luminescent powders is available. Wet non-porous surfaces at a crime scene can be treated using the SPR or the small particle reagent and a suspension of the molybdenum disulfide in a detergent solution. This is the SPR reagent. The suspension is generally applied with a sprayer and then rinsed with water so as to remove the excess powder. The developed prints are dark grey in color. A white small particle reagent based on zinc carbonate powder has also been developed for the dark surfaces. Cyanoacrylate esters sold commercially as the quick setting superglue have proven effective for developing latent finger marks on non-porous surfaces. The object is treated with cyanoacrylate vapor, resulting in the formation of a hard white polymer on any latent print deposit that may be present over the surface. It is believed that the polymerization is catalyzed by moisture and the ionic material present in the deposit. Fuming with cyanoacrylate can be achieved by several means, from inexpensive homemade chambers through to large, expensive commercial units. Portable fuming systems are also available, as opposed to development achieved at atmospheric pressure. A number of research groups have reported superior results when cyanoacrylate development is conducted at reduced pressure. Contrast is often a problem with marks developed by cyanoacrylate fuming, and some form of enhancement is generally required. There are optical methods for enhancing such prints that should be employed before any further processing of the fingerprints are done. Also, contrast may then be improved by the application of a powder or preferably by the application of luminescence stain such as rhodamine 6G. Luminescence staining can significantly enhance the cyanoacrylate developed prints. Probably the most sensitive technique for fingerprint detection on non-porous surfaces such as glass and plastic is a vacuum metal deposition. In this process, the item is placed under vacuum and coated with thin layers of gold and zinc preferably. The deposited gold penetrates the latent fingerprint residue or the deposit, producing a uniform layer, whereas the zinc will generally deposit on the substrate but not on the print ridges. VMD units necessary for the application of this technique are expensive and their use requires significant experience for the optimum results. When applied correctly, excellent results can be obtained even on old degraded finger marks. VMD can be effective on difficult surfaces where other techniques fail completely. This substrate, because of its semi-porous nature, has proven difficult for the latent fingerprint detection. Prints more than 6 months old have been developed using this sequence. Cyanoacrylate fuming alone will only detect prints that are up to 1 week old. Next is the fingerprint detection at the scene of crime or crime scene. The general approach to fingerprint detection at the crime scene is to apply optical techniques initially so as to transport the items back to the laboratory for processing where possible and to treat the remaining surfaces with a suitable development technique or a sequence of technique. For non-porous surfaces, the fingerprint powders are traditionally the method of choice. Porous surfaces such as wallpaper can be treated with ninhydrin solution. For scene of a more serious nature, chemical processing with a technique such as the iodine or benzoflavone spray may also be considered. This technique can be successful on developing prints on a range of porous, semi-porous and non-porous surfaces. In addition, the iodine or benzoflavone treatment does not preclude subsequent powdering or ninhydrin treatment. At the end of the sequence, the blood enhancement reagents such as amido black may also be applied if blood marks are present at the scene of crime. Now students, let us summarize this module. Fingerprint detection has improved significantly over the last 20 years due to concerted efforts by a number of research groups around the world. A wide range of optical, physical and the chemical technique is available for the detection and enhancement of latent finger mark. Today, for the purpose of fingerprint detection and enhancement, polylite is used. The alternatives to polylite include the specs, quasar, the ductilite and the portable lasers such as scene sweeper. Lasers are restrictive in that they only operate at a limited number of wavelengths. Finger marks treated with ninhydrin can be further enhanced by treatment with zinc or cadmium salt solution. Cyanoacrylate fuming has since the late 1970s become a popular laboratory-based technique for the routine treatment of non-porous surfaces. Developed prints can be subsequently enhanced by the application of a luminescence stain. Contrast is often a problem with marks developed by cyanoacrylate fuming technique, and some form of enhancement is generally required or needed for that purpose. There are optical methods for enhancing such prints that should be employed before any further processing of the finger marks is carried out.